Alright, so this is the first video for chapter 4. So we're moving on now into sort of the algebra portion of Math 1410. We're moving away from the complex numbers, from the vector geometry, and we're moving into the actual algebra part. So we're going to introduce matrices and look at the algebra of matrices, and we'll see that as with vectors, we can define addition, scalar multiplication. We'll also see that you can multiply matrices, which is not something you can do with vectors. I mean, there are certain vector products. There's a dot product, there's a cross product, but there's sort of a natural multiplication that you can define for matrices, and we'll be seeing that as well. But first, we'll just introduce the basic idea of what a matrix is. So a matrix is simply an array of numbers, okay? It's a rectangular array, so you take a bunch of numbers and you arrange them into some number of rows and columns. You can consider matrices over different sets of numbers. You can consider matrices with real entries, with complex entries, and so on. We will almost exclusively deal with matrices that have real number entries. So here are some examples of different matrices of various sizes. So this matrix A, for example, we can see that it has 2 rows. Okay, so the rows are the horizontal, the columns are vertical. So there's 2 rows, 3 columns. So this is a 2 by 3 matrix. 2 rows, 3 columns. In general, when you're specifying the size m by n, m refers to the number of rows, n refers to the number of columns. So B, we can see that B has 1, 2, 3 rows and 2 columns, so this is a 3 by 2 matrix. The matrix C has 2 rows, 2 columns. It's a 2 by 2 matrix. This case, by the way, where the number of rows is equal to the number of columns, these are referred to as square matrices. So m is equal to n in this case, right? Both of them are equal to 2. So square matrices will be important later on. So there's language for them because square matrices have certain properties, and there are certain things that you can do with a square matrix that you can't do with other matrices. So if we want to refer to the particular entries of a matrix, we can talk about the ij entry. Okay, I'll use this notation. You'll also sometimes see this referred to as maybe the ijth entry. That's another term you might hear. It's, I don't know, this is sort of a mouthful, I think, ijth entry or ij entry. In any case, we're referring to the particular row in the particular column, right? So for example, if I wanted to tell you the, say, two entry of A, well, that would be, so I would say I would go row 2, so row 1, row 2, row 1, row 2, column 1, column 2, column 3. So I go to the second row, second column, I'd see what number is there, and I see that I get a minus 2. Okay, and if I wanted to know what is the, let's say the 1, 3, that's not going to work. The 1, 2 entry of B is going to be, well, let's see, I go row 1, column 2, and there's a pi sitting there. So the 1, 2 entry of B is pi. In general, sort of general notation, we can write, say, aij for the ij entry of A. In this notation, one of the things you'll often say, okay, so you'd write A as sort of the matrix aij. We'll see this shorthand notation quite a bit. It simplifies a lot of the discussion. Okay, so why do you consider matrices? Why are they useful? Well, there are many applications where matrices come up. You don't have to search very hard to find applications of matrices. Well, a quick Google search for applications of matrices will, I'm sure, find you a number of examples. You'll find matrices in use for computer graphics. If you want to encode computer graphics, much of that is done using vectors and matrices. Any sort of data mining, data analytics, you'll see matrices in use there. Adjacency matrices for graphs and roads. I mean, this is an interesting one where maybe you've got a number of nodes with labels, maybe 1, 2, 3, something like this, and then you've got connections between the roads. So maybe the connections are just telling you how far. So maybe the 1, 2, 3 are labeling cities, and the connections are distances. So maybe the distance from 1 to 2 is, I don't know, 17 kilometers. The distance from 2 to 3 is 21 kilometers, and the distance from 1 to 3, maybe that's I don't know, 30 kilometers. And if you wanted to kind of keep track of all of this information, you could write down a matrix, and maybe you decorate that matrix, but you don't necessarily have to decorate it. So you can put your 1, 2, 3, 1, 2, 3, labeling the rows and columns. And in each entry, so the ij entry for this guy, here the ij entry is going to be the distance from I to j, right? So everything, of course, has distance 0 from itself, so you would get zeros down the diagonal, and then you see the distance from 1 to 2, well, that was 17. And then, of course, the distance from 1 to 2 should be the same thing as the distance from 2 to 1, so we get a 17 in both spots. The distance from 1 to 3 is 30, 30 down here as well, and then 21, 21. And so you can fill something out like this. And there might be scenarios where, maybe you're dealing with one-way streets, or, there might be, the way to get from 1 to 2 might be different from the way you get from 2 to 1, in which case maybe, this number and this number are not the same. I've drawn a scenario where you're dealing with two-way streets, so those numbers are the same. Or maybe this is not, distance on a road. Maybe this represents some kind of, like different states of some system, and these are, I don't know, energy levels or something, and you increase by a certain amount going from 1 to 2, and then if you went back from 2 to 1, you would decrease, and so you would have, say, a plus 17 in one spot and minus 17 in the other spot. There are lots of possibilities where this might come up. Another big one, if you're ever curious, you might want to go and find some articles kind of explaining the basics of how the Google PageRank algorithm works. Now, there's a lot going on there. It's much more complicated than simple linear algebra, but there's a gigantic matrix with billions of entries that Google uses to keep track of how different websites are related to each other. Roughly speaking, this is a bit of a simplification, but this is one way of thinking about how Google does its things. There's a lot of sort of matrix arithmetic involved in things like air traffic control, things like this. And some of these are big problems. These are ones that you're not going to do by hand. You're going to use by a computer. And even with a computer, you might have to come up with very special algorithms to do things quite quickly. You can imagine that, Google search algorithm, right? Nobody's happy if it takes more than 2 seconds for their results to show up on the screen. Air traffic control, if you don't get to your answer quickly enough, then even worse things might happen. So essentially, you're using matrices to organize data, right? And you might be using matrices to kind of organize data that tells you about relationships, right? You can see this in this adjacency matrix. These numbers are telling you about how different locations or different states are related, right? Distance between them, something like that. We can look at some other examples perhaps, but let's sort of introduce some general notation first. So as we mentioned, you can talk about the ij entry of a matrix. So this is something which is, remember, this means row I column J, and so the rows are the horizontal guys, so you have row 1, row 2, down to row M. These are your rows, and then your columns are going across, column 1, column 2, all the way across to column N. Those are your columns. And so often, and especially when you want to write down kind of definitions and proofs involving matrices, in a later video we're going to talk about things like matrix addition, scalar multiplication, and you want to, define these things, and you want to define them as generally as possible, right? You don't want to have to write out a big mess like this every time. It takes up too much room on the page. It's much nicer to simply write something like this. A equals Aij with the square brackets around there to tell you that you're talking about a matrix. And sometimes you might want to decorate this notation. You might want to say put m by n if you want to specify the size, or maybe you want to be even more explicit, so you want to say it's a matrix Aij where like 1, so I goes from 1 to m and j goes from 1 to n, something like that. But normally, once the context has been established, you don't really need all of this information. You can just use this sort of basic notation here. Okay, moving right along. If we want to talk about matrices, we want to establish properties of matrices. Well, one of the things we need to be able to do is say what it means for two matrices to be equal. So, when you think about equality is something you're quite used to, right? If I wanted to write down a definition of what does it mean for two numbers to be equal, you would probably find it kind of silly to even bother, explaining, what does it mean to say that two numbers are equal? It means they're the same number. It's equality with numbers is something which is so natural we don't even really bother to define it. But once you get to something like a matrix, a brand new object, and you want to say, well, you have to actually specify what it means for matrices to be equal. So, what does it mean to say that two matrices are equal? Well, first of all, they have to have the same size. And for two matrices of the same size, equality means that they have the exact same entries, right? So if I have two matrices A and B, so A, I write the entries of A as Aij, I write the entries of B as Bij. A and B have to have the same number of rows and the same number of columns, and if I choose a particular row and particular column, I have to find the same number sitting inside of the matrix A as I find inside of the matrix B. So this is a pretty straightforward definition of what it means for two matrices to be equal. And of course, if all the numbers are filled out, this is kind of an obvious thing what that means. But we'll want to be solving equations involving matrices, and we want to be able to make definitions, and we want to say, make a definition where we say that a certain matrix is defined as being equal to some expression involving other matrices. So we need this notion of what matrix equality is. Okay, so that's the basic idea of what a matrix is. We're going to continue in the next video to talk about addition and scalar multiplication.